Today's what day is it today? It's 9th February. Today is Thursday. So last time we saw a theorem which we did not state completely correctly. So I'll try to go over the proof of that once again. So it was roughly, I will not state it fully. R2S is an extension such that R is strongly F regular and S is finitely generated. Then R splits of S. Suppose this map is I. So we need I to be injected. And yeah, this is algebra map. So I'll present a proof of this and I'll try to highlight why certain steps work. So this assumption is necessary because of this counter example which was discussed. Take polynomial ring. Take you take this. Suppose this is basically polynomial ring mod X. Yeah, so this will not split as FPX modules. So it doesn't split. But last time we saw that regular local rings or regular rings are strongly F regular of characteristic P. So this being a regular ring, if at all this theorem was true, this should split without the assumption if I was injective. So now we assume that I is injective. And so I will just show the proof. What we did was, so we first observed that splitting is a local property. So we can assume that the rings are local. But being strongly F regular is also local property. And it was observed in a lemma that local strongly F regular rings are domains. So we reduced it to this case. Yeah, let me state it. So we reduced it to this case R2S, and this is local and a domain. We are also assuming this is F finite. But this ring may not be a domain. So we had this R2 map S, and we said that suppose we go mod a minimal prime. This is a minimal prime of S. Then this composition may not still be injective. So if at all we say that we can reduce the theorem to this case, we should prove that this composition is injective. So that's what I will prove now. And yeah, so it is a consequence of going up, going down type of those four results. So first of all, we observe that since P is minimal, it contracts to zero. But S is a finitely generated module over R, so hence it is integral. And therefore, we have that this is the unique extension of zero. So basically, what this says is P intersection R is zero. That's what we want. So the kernel of this map S to S mod P is P, but that does not intersect the image of R. So we have that R to S mod P is injective. And now we have reduced to this case where R is local ring under domain and S is also a domain. And then what they claim is form R, S comma R is non-zero. This is because S and R are domains, so that annihilator condition is trivially satisfied. Annihilator of S is zero, annihilator of R is zero. Because annihilator of S in R is zero. So there is no non-zero division on R which lies in the annihilator. So there is some non-zero form. Let that form be theta, is what they call from S to R. And theta of 1 is C. Suppose. Yeah. Then the next step is to and yeah, C since R is a domain and C is non-zero, C does not lie in any minimal prime of R. And now the assumption that R is strongly F regular gives that there exists a E such that the map R from R to Fp star R sending one to Fp star C splits. Yeah. And so then we can consider this diagram. R to S there is a map. R to Fe star R there is map. And R S to Fe star S there is a map. Fe star R to Fe star S there is some natural map induced from this. Suppose this map was phi. This is Fe star phi. And suppose this map is psi. And then what do we have? Since form SR is non-zero, since form SR is non-zero, there is theta will induce a map from Fe star S to Fe star R. Suppose that Fe star theta. And this map also splits. Suppose that splitting is phi. Then phi compose Fe star theta at 1 is so Fe star theta takes 1 to Fe star C and theta of Fe star C should be 1 since phi is a splitting of psi because 1 goes to Fe star C then Fe star C should come back to 1 since this is a splitting. So we get that this map is also splitting from so this map then so this gives theta compose Fe star phi compose Fe star theta is a splitting from Fe star S to R. But since this diagram is commutative, the map psi also splits via this long path. So this gives that R to S splits.
What is theta again?
So yeah, so we first observe that form S comma R is non-zero. So we take any non-zero element in the
Oh,
form.
you take any non-zero element in form. Okay.
Yeah. So suppose theta 1 is C. And yeah, so this C due to not lying in any minimal prime induced us that
Why is
induced
it
a split.
non-zero? Sorry. Why is it
Uh,
non-zero?
because if theta 1 is 0, then everything becomes 0.
Yes.
Therefore, but we picked a non-zero element in the form. Oh, you want why
Uh,
this form?
why this
Oh,
form
okay.
itself is non-zero? Yeah.
So because annihilator of S is so there is some condition I think. If I remember it correctly, I can state it. So this is form R m comma n is 0 if and only if n contains, or yeah, I think annihilator of m in R contains a non-zero divisor on n. I think this is correct if somebody can confirm.
Yes. Yeah, yeah, yeah.
So form R of S comma R will be 0 if and only if annihilator of S in R contains a non-zero divisor on R. But in our case, annihilator of S becomes 0 and
Yes.
0 is not a non-zero divisor.
Yeah.
Yeah,
So,
so mhm.
uh, another question is, oh, why is splitting a local property? So, more precisely, suppose you have a ring map R to S, say it's an injection. R is contained in S such that R localized at P inside S localized at P is a split map for all primes P in, I don't know whether you take it in R or S. Let's take it in R for now. Then how do you define a map from S to R? And this map must be an R module map such that, at every localization, then you can say using kernel and co-kernel, you can say it's different. But how do you define this inverse map?
Yeah, so what I said was not completely precise. Well, the precise statement is suppose R to S is a map such that S is finitely generated, then splitting is a local property.
Uh, okay.
And yeah, so I think the argument somehow uses that which was seen before. Spec R is quasi-compact. Actually, yeah, so I did not check this completely, but there was this idea.
A car being quasi-compact does not require S to be finitely generated.
Yeah, but I think what they do is suppose there are only finitely many localizations about which you care, then I think there is some easy way to define.
No, finite generation is a stronger condition because for any ring, spec R is going to be quasi-compact. Whether the
Yes.
ring, yeah, that is not a problem. I guess
Yeah.
being finitely generated, you can. Uh, so my whole like concern is like, how do you define? Like, how do you get a well-defined map from
Yeah.
S to R? Because if R to S is an injection, right? S to R is a surjection.
Hmm.
And in surjections, you do have a choice.
Yes.
Like your element is okay, maybe not. Ah, maybe not. Okay, yeah, that is the issue. Like we have to get a well-defined map from S to R and say uh, suppose the element is an element X in S. It's if it's so first of all, what if it's a yeah, okay, maybe we can think about this later. Yeah.
Yeah. You should think about it. Yeah. So this highlights. So yeah, then I think we can straight the corollary out of this. R to S, the map R is irregular. Then this splits. Assuming injection and finite generation. So this property holds true in general. This stated. So this is a general result if R is regular and R to S is finite injective map, then I see. Yeah. So this is a general property. But if the ring is a positive characteristic, then we have a proof of this property. Assume, yeah, and this proof relies on Kunz theorem also. So that is actually nice. Yeah, so I had, I think, mentioned this while discussing weekly F regular rings, but yeah, we can mention it for the strongly F regular rings. So RBF finite, strongly F regular, then R is normal. So yeah, normal means integral closed in the field of fractions. So suppose R is not normal, then yes, yeah, I think there is no assumption for it to be local, right?
No, because normality is a local property. So you may as well assume all these things are like other than finiteness. If R is finite, then R localized term is finite. But strong F regularity is a local property. You can localize it and you can show that, and then yeah, you can work with a local ring, and then it's a domain.
Yeah, yeah. So yeah, that's what I saw. You can say domain. So then, yeah, let X be in quotient. Well, I should write let X be in R. Oh no, it's correct. Let X be in quotient field of R. That's that. X is integral over R. Then we have this finite extension R to Rx. But yeah, so I think I need something more. Or no, yeah, that's what I proved no, in the last thing. Strongly if regular, everything splits. Yes, yes, yes. Nice. So this is strongly if regular. So this means this map supposes I, the natural inclusion, splits. So there is a map from Rx to R, such that one goes to R. Suppose phi, which is R linear. So phi at X may go to something, say C. Then since X is in the quotient field, I can write X as A by B. This means that P at A by B is C. I can multiply by B. So B times P at A by B is P at A, which is A because A lies in R. This gives P at A by B is A by B. But P is a map from Rx to R, so A by B must lie in R, which is X. So X lies in R, so X is a normal ring. And yeah, so this proves that strongly irregular rings are normal. Yeah.
Uh, just a question. So did we already prove that weakly F regular or normal when it's local? I mean,
Well, I had not proved, but I had mentioned that
yeah.
that property does not require strong F regularity. In fact, it is true for weakly F regular rings. The proof is slightly different, I think. I mean, at least this will not work.
Okay.
So I think the next theorem is really important. Theorem is so dark. Because direct summand of strongly F regular is strongly F regular. First, this can be stated as a slogan. The precise statement is suppose R, S are finite. R is splits of S, or R is a direct command of S. This is only F regular. Since so is R. So yeah, what will this prove is that so many rings which we know are strongly F regular. So if this ring, suppose K X square Y square is strongly F regular. And K is some field of characteristic P. I can take anything K X square X Y Y square. Well, I don't think it's direct summon. Direct summon is module. It is no. I don't mind out this because it's not Vahan Macaulay. Oh, sorry, I'm very sorry. Some other reason, suppose X Y. This is also strongly F regular. So since polynomial ring is regular and hence strongly F regular, such kind of rings are strongly F regular. In many cases, maybe this is also strongly F regular. The fixed field of some group that may also induce certain invariants, invariant one, some invariants, suppose N. And this is a direct command of polynomial ring. Yeah, one has to check something, but suppose this is, then it will automatically be strongly F regular. So this actually is a nice theorem to prove some things. So yeah, so there are two theorems which I think are very useful for these things. So let me prove this. So once again, since strongly irregular is a local property, we may as well assume that the map from R to S is local. R and S are local, sorry. So let me prove this. So R to S, suppose this map is phi, this phi has a splitting. then I can assume R and S are local rings and S is strongly F regular. But yeah, strongly F regular ring. Well, yeah, so what I can assume is R is local. So I will look. So what will this be? We'll go to RP, SP, where P lies in spec R. This 5P. This ring I can assume to be local since
Uh,
S is
I think you may want to take localization with respect to S instead of R. Because S localized that uh, P is a prime in R. We are inverting some elements of R, but why should that make S a local ring?
yeah, so S
Or
is not a local ring. So actually I'm inverting a image of this set R minus P.
Hmm.
I'm inverting this set in S after taking image.
so what I'm saying is, what if you take a prime Q in S and take its inverse image in R and then localize with respect to these two, this Q.
Yeah, we can do that.
So does that preserve the splitting?
It should, I believe, because identity goes to identity.
Huh?
So there is a reverse map. Suppose phi,
Yeah.
then phi compose psi is identity on R.
Yes.
Then if I localize it will still be.
Okay. Okay. Yeah. So no. So my concern, like why I don't remember it now, but if we are going to use anywhere that S is a local ring, or maybe that the map phi is a local map, you may need this. You may need this second localization is the first. But yeah, let's go on with the proof. I don't remember it now.
Yeah.
You can erase this one and then proceed with the usual proof. No, proceed with the usual one. We don't have to.
What? So yeah, since you are asking, so I remember. So strongly if regular is a local property. So we need to prove that RP is strongly if regular for all P in spec R. If we prove this, then we are done. So yeah, we can localize at a prime of R. Suppose this map is psi. I can assume this to be domain. Oh, well, no, we can assume this to be local. But this is strongly F regular. So SP is normal, first of all. But there is some fact. Fact. Normal is product of normal domain. So SP can be written as product of say SI. Yeah, I say suppose from 1 to n and denote by EI this number 0 1 highest position 0 like this. Then what we have is that we first of all have a map like this, RP to SP. What was the name? I forgot. File was 5. And there is a splitting. Suppose that is psi p. Then psi p at 1 is 1, but 1 is summation of ei. So 1 here will be psi e1, psi p e1, da da da, plus psi p en, suppose. But since R is local, one of those, so one of psi p ej is a unit. So what I can define is, so I can define this map. Well, this was Sj to R. Suppose I want to define a map, I can define to be, so this psi tilde at Si is this map, psi p at Sj, sorry, Sj. This is a very defined map. Also, can you say this is surjection? Psi tilde is surjective. This is clear because at 1 this goes to some unit. So multiply by some unit, you will go to some unit. You will go to 1 and then you will have everyone. So this gives surjection Sj to R. This is R linear. So R to Sj, there is a map where one goes to, what was the thing? Phi, no, maybe, yeah, phi. So that is 1 went to 1. So 1 went to Ej. And then there was a splitting which was psi, where Ej went to 1. Yeah, so I think, yeah, this itself is a splitting.
EJ does not go to 1. EJ goes to unit.
Oh, yes, you are correct. So I have to define, suppose Ej goes to a unit U, then what I should define, this is U inverse psi. That gives us splitting. Psi, the splitting of phi. And this is R linear because of whatever argument we gave. Here. So this gives, so since Sj is a normal domain, we have Sj is also localization of S. S R to S, where S is strongly F regular. The domain and R is a local ring. We can assume S to be strongly irregular because this is
One second. Yes, J is a normal domain. Yes, but why is SJ strongly irregular?
so Sj is a localization of S. This is because
Localizing at. Okay.
so S,
Uh,
this is S1 cross S2 cross da,
okay,
cross
okay.
Sn. So I can take the
Okay, you're using
primary.
that. Okay, yeah.
So now in this case, what we take is let C be in R0. Map from R to S. Suppose this map is phi. This map is clearly injected. So I can view correct? Correct. Yeah, phi of well, yeah, I can view C as an element of S because it's an injective map. That's what I want to say. But then C will also not, since C is non-zero, C is non-zero, and this map is injective, image of C is non-zero. But S is a domain, so phi of C lies in S0. And therefore, since S is strongly irregular, there exists E positive, and yeah, what do I use? Uh, Map alpha from P star S to S such that P alpha at P star C is 1. And when I say P star C, I mean phi at C. So yeah, this is a splitting of the map S to Fe star S. But yeah, S to R is also a splitting. There's a splitting like this, Fe star S. So there is some map there. So hello. So map, which is natural psi map. There is Fe map, Fe star. So the map, there is splitting of this map. R to Fe star S. So what this gives is alpha gives us splitting of R to Fe star S. But since R to Fe star S splits, we can look it as composite of this map R to Fe star R to Fe star S. Since this splits, we have R to Fe star R splits. But now I may ask the question, what is the image of 1? So yeah, since this map was injective and 1 went here to 1 went here to Fe star C. Since this map splits, this composition is injective. And yeah, so this composition is injective. One here goes to Fe star C. So it must go Fe star phi C. It goes Fe star C here. Right? What is the argument? Composition is surjective, injective, sorry. And therefore this map is injective. And what else can I say? If this map is injective and if
Okay. P is a splitting. P from R to S is a splitting. So you can apply Fe star and see that Fe star phi is also a splitting of Fe star R module.
yes, yes,
Phi is a splitting of R modules, therefore Fe star phi is a splitting of Fe star R module.
yes,
So that should help.
yes. So yeah, it takes Fe star phi C2, Fe star 1. Oh well,
No,
sorry.
no. So your
Yeah,
C
it
is in
takes Fe
R.
star C, yeah.
Your C is in 1. Yeah, you take Fe star C and then apply the splitting map to see that this element, there is a splitting which splitting of Fe star R modules, hence of R modules. So the whole composite, you get the same Fe star C back. And you know that R to Fe star S is also a split map. Uh,
Hmm.
R to Fe star Fe star S, yeah, composite is a split map. Yeah.
Yeah, so
Essentially,
components.
what you have written is a sort of like a Cartesian diagram, right? So you fill in the fourth coordinate as quadrant, fourth, uh, and the bottom left as bottom right as Fe star R, and
Are splitting maps. There is this map, but there is a natural splitting. This also has a splitting, so this gives a splitting like this. But since this has a splitting, this also has a splitting.
there are three split maps, so the fourth one must also be split. That is the whole point.
So this must also be split. This what is the here. Yeah.
So
This
you want to know what
this
the
composition, yeah.
you want to know what the image is. So the image is going to be you take one in R to one in S. One goes to one. One in R goes to one in S. And
Fe star phi C, yeah.
phi C, yes. And yeah, and then you use the fact that it's a splitting to get this back.
Yeah,
And so yeah.
yeah, yeah. This helped a lot, yeah. Yeah, so this gives. So this gives what does this give? R2 Fe star R, one going to Fe star C splits. So this proves that R is strongly irregular. Yeah. So this ends the proof of that theorem, and I think now it's done. There is one more theorem which I think I can do, or I can solve some exercises. So yeah, let's try to solve the exercises first. This is the exercise. And yeah, Abhiram had sent some exercise. All of them discussed.
Oh no, we did not discuss that.
Then I think we can-
I don't I don't think anyone. I don't know if people are interested in that. Mostly like the other essays are very, first four questions are very not very difficult. It's the fifth and sixth which I found interesting because it talks about something more.
Yeah,
Oh wait, no, not even. Can
this is, yeah, sixth is something. Fifth is something, yeah.
fifth basically says that you can finiteness is a you can without loss of generality assume that it is reduced. So that is the whole point of the fifth
Yes.
exercise. And the sixth one is where the test element comes in. There are two results which are analogous to Krull intersection theorem and Nakayama lemma. So
Hmm. Okay. I think we can do fifth and sixth. That's okay.
so
But
Yeah.
yeah, third was used, I think. Proof.
in the proof, yeah.
Yeah. So yeah,
That
these are
part is very it's standard, yeah.
and the
Yes.
second is not strongly F regular, that's also known, I think.
It's not strongly regular. Why?
Because Y is not tightly closed. Came out like that, no?
Oh yes. Yeah. It's not even weakly regular.
Yeah.
Yeah.
Yeah. Um, oh, the scores. Yeah. Oh yes. Yeah, this I think. Yeah, this I had some doubt in understanding this, but this exercise made it clear.
When I typed this question 5 like 1 month before, I assumed that the there is a part C to this question, which I assumed was like a very it 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 is some complicated result and so on. So I I put it as a question and I was not completely sure if that is correct, but yeah, that's why I gave an open-ended question. Suppose R is finitely generated RQ module, uh, not necessarily reduced, is R an F finite ring? Meaning, do you uh, do you n- need a reduced property? Uh, so this is not true for flat uh, rings. The previous example, it is that R to R inside, if you have a ring map R to S, uh, it could be, that, sorry, there is no ring map, yes, sorry. So it could be that R is flat over R power P, but R need not be a flat, Frobenius need not be a flat module. Frobenius may have a flat map, yeah. But my question at that time was whether um, the same holds for the finiteness property, a finite property. So at that time, I was a bit uh, confused. Like I was not sure. But later, while I was doing this Gabor's theorem, I realized that this is not a very deep question because so if you can you write that below? So
Yeah.
what I'm trying to say is um, what is the so R to Fe star R. Okay. You don't even need a E. So you just take R to F star R. This is the Frobenius map. Yeah. Uh, and then um, mm, and then draw a commutative diagram. Um, so below this map, you can write the image of R, f of R. Hello? Hello, Acha? Can you hear me?
Yeah, I can hear.
Okay. So maybe it's connected. So the idea was that you can always factor a map, factor a ring map R to S as R to the image phi of R, and then image is sitting inside S. So you can factor it as first a surjection, then an inclusion, right? And the surjection map is always a finite map.
I think
By
Aditya left the meeting.
Oh, so there may be some issue with this internet.
Yeah.
So R to phi of R will always be a finite map because it's it's a surjection. So that is always true. And so the ring map R to S is a finite map if and only if the inclusion is finite. So if you apply this to Frobenius, then the Frobenius map is finite if and only if the inclusion R power P inside R is finite, which means that R is finitely generated as an R power P module. This is not the same for, this is different from flatness, because in flatness, even if you decompose it, okay, he's here.
Yeah, so my network got some issues.
Yeah. So here,
Mm-hmm.
so for a general ring, let's take a general ring, R to S ring map.
Yeah.
Okay. And you can factorize this ring map as first a surjection, then an injection. So
Yeah.
if the map is phi, then R to S phi, phi of R, and then this goes to S, right? So this R to S, the composite is a finite map if and only if the inclusion is finite. Why? Because the surjection is always finite.
Yeah.
Surjection is always finite. So phi is finite if and only if the inclusion of phi of R inside S is finite. So
Yes.
apply this to the Frobenius. So
Yes.
image of the ring is R per P. So
Yes.
all I'm saying now is the Frobenius map is finite, that is R is F finite if and only if R is generated, finitely generated as an R per P module. And that was question, the part C of the thing. When I was looking at the exercise, I thought it's going to be some complicated proof, but it is not.
Yeah, but this is a nice fact, I think. Yeah.
And
Yes.
it is not always true for other properties, like with flatness. The reason it worked for finiteness is because the surjective map is finite, but the surjective map is not flat most of the time.
Yes. Yeah. So we have to show that Frobenius is finite if and only if it is finite for some high enough composition. But I think we can try to use this now, yeah. So R is F finite. If and only if R is finitely generated over RP. So if R is F finite, then some high enough power Frobenius map is also F finite. But I think then I need to prove that maybe this can be a lemma if R is generated by, suppose, alpha 1 to alpha k over Rp, then R to the P is generated by alpha 1 to the P, alpha k to the P over Rp square, and so on. And so on. Suppose if this can be proved, well, and suppose the Rp is generated by these people, then R is generated by these people. Suppose the converse is also true. Then I think we can give a proof of this in some other manner.
You don't need the lemma.
Yeah.
You don't need the lemma. So idea is, if R is finite, then R is finitely generated over R per P. Okay.
Yeah, that is
If and only if that is the condition, right? So if F is a finite morphism, composition of finite morphisms is also finite morphism.
Yeah.
So Fe is also a finite morphism for all E greater than 0.
Yes.
And that is one, therefore, Fe star R is a finitely generated R module. That is one direction of proving.
Yeah.
For some large E. That was the question, right?
Yeah. So yeah, suppose some Fe map is finite, then the F map itself should be finite.
And then how do you show that?
Yeah, that we need to show now. So suppose Fe map from R to Fe star R is finite. Then need to show that F is finite. But I have this R, F star R, and so on, further composition. If the whole composition is finite, then maybe I can write it like this and proceed by induction somehow, that Fe minus 1 star R to Fe star R. So this whole map is composition of two maps. Suppose this is Fe map. So this is composition of some, say, alpha and Fe minus 1. And if this is finitely generated as an R module, this is finitely generated as this module also. So alpha is a finite.
Yeah, but you don't need induction again. This is very straightforward. So now this is
Yeah,
where
I mean, we can decompose like this, you're saying, R to F star R and the forward map.
you don't have to decompose it. There's no need for that. So Fe star R is a finitely generated R module, which is saying that the Frobenius map F power E is a finitely generated. It's a finite morphism. That is clear.
Yes.
Again, now we apply the if and only if condition that I mentioned, which is saying that this happens if and only if R power P R is a finitely generated R power P power E module.
Yeah.
Right?
Yeah.
But R power P power E is contained in R power P, which is contained in R.
Ah,
So if
okay.
R is finitely generated over R power P power E, it must be finitely generated over R power P. That is exactly the condition that R is finite.
Oh, yeah, okay. So this gives it very nicely. Yeah.
Yeah, you don't need.
Yeah, it's very nice. I show that F finite. I think if we prove it for some large enough E, then it is okay. But for
For
large
any
enough,
one,
yeah. But for large E, I think the radical of 0 goes to 0.
are you
So,
talking about B now?
yes, yes.
Okay. Yeah.
So we can assume a finite ring is reduced. So, so I can look at very large E. Suppose this map Fe, where E is large. Then kernel of Fe is radical of 0. I can assume this. And yes. So I have this map, which you have mentioned as in the hint, R mod radical 0 to Fe star R. The map Fe. This map is injective at least. There is a natural projection.
Second map is not an injection, but because the whole map is a finite map and the first map is a surjection, therefore the Fe map from R reduced to Fe star R is also finite map. Yeah.
It's a finite map. I think it's injection, no? Because more than radical 0, there is no kernel.
Yes, but why do you need injection for this?
We don't need, yeah. I'm just mentioning it.
Yeah.
Yeah, we don't need it. Yes. Then you're saying consider filtration, each finitely generated.
Oh, okay. Yeah. So actually, you shouldn't. There is a map that you wrote, right? R reduced to Fe star R. So
Yeah.
there is another map which is again trivial, but you have to mention it, which is that Fe star R to Fe star R reduced. So you have to look at that map. You're making a claim on the Frobenius of iterated Frobenius of R reduced. So yeah. So again, this map is finite because this map is surjection. Fe star R to Fe star R reduced is a surjection because R to R reduced is surjection.
Yeah, so this, yeah, R reduced to Fe star R reduced, is that finite directly, I believe?
Yeah, that is finite because Fe is a finite map and the next map is a surjection. So yeah, both are
Yeah,
finite, therefore the composite is also finite.
yes, yes, yes. So
This shows that if R is finite, then R reduced is finite.
yeah, and then we can go to the convert. Suppose R reduce is a finite. Yeah. Then we don't know if this map is finite, but this map is for sure finite. And the big map is finite. Yeah, so yeah, let me write it separately so that it's clear. So peak E large such that R2 are reduced to Fe star R, Fe star R reduced such that we get, and this composition is finite, and this is surjection, and this is also surjection, this is the injection. Now we need to prove that R reduced to this is finite. So we need to show yeah. So
I think this is where you need the use of hint.
yeah, that you had mentioned as hint, no? That we have to consider a filtration such that each is finitely iterated. Yeah. J to the yeah, let's do this. Then what do we have? We have this.
It's not radius, it's an R. J is the nil radical.
Yeah. So the last thing which we have is 0 to j to the n minus 1 to j to the n minus 1 by j to the n minus 0. We need to show that j to the n minus 1, this Frobenius functor, is finitely integrated as R reduced modulo. And this is clear because this is 0. Yeah.
This won't generalize well. So how do you get a map from the next one again? Because so you
Yeah, this may not work here now. No, what may happen?
so these factors they come up in a different setting. That setting is so what if you have a map from R mod I to R mod J? What is the kernel of that map? It's
Mod I.
that exact sequence. So I'm saying you take R mod J power from I to J power I plus 1.
Yeah.
Yeah. That this is that exact sequence.
Yeah.
Yeah. So not just necessarily N. Just
Oh yeah,
make it some.
let it stick to be K.
Yes. Yeah.
J to the K is a smaller ideal, so this ring is big.
J power K minus 1 modulo J power K.
Yeah. And suppose we prove, yeah, this Frobenius of this is 0, right?
You are not applying Frobenius. So
Uh-huh.
first consider K equal to N. What is it that
Yeah.
you get? Yeah. When K equal to N, what do you get?
This is R.
Yes.
This is R mod some power of radical,
Yes.
and this is again radical, some power of
Yes.
radical.
So what if k equal to I guess 1?
Yeah, k equal to 1.
1 means what is j power 0? J power 0
K
is not
cannot be
defined.
1. K, suppose k
2.
is 2.
Yeah.
Oh, this is ulta, no? K minus 1.
Huh?
K minus 1 is a smaller ideal, so this is a bigger ring. Yeah. Yeah, now this is correct.
No.
Oh, well, yeah, why I'm so confused?
No. So j power k is contained in j power k minus 1. Erase this,
Yeah, okay,
erase
so
the
yeah, this
power.
is. Yeah. True.
So
This
j
is
power,
j square. This is j mod j square.
yeah. Okay. Now can you erase this at the top? Okay. So okay. So not everything. Okay. Yeah. Aditya,
Uh-huh.
you here?
Yes, I can hear you.
So where is that exact sequence for all k, for general k?
Oh yeah, that I think was erased. So this is R mod j to the k minus 1 by j to the k.
Yeah.
R mod j to the
K.
k to R mod j to the k minus 1
Yeah.
to 0.
To z. Yes. So okay. Now applying FE star to this is still exact.
Yeah.
Oh, what is the background noise?
So somehow
So now,
automatically it started.
yes. Okay. So now take k equal to 1 because when k equal to 1, what happens?
Well, I think we want this R mod j to R.
R mod j. That is the only thing, and this is not very useful. Yeah.
We want R to
So
R mod j maybe, yeah?
R to R mod j, which is R reduced.
Yeah. This is R reduced.
Because wait. Yeah. So FE star, so if k, did we take k equal to 1 or 2 now?
I think we just
Okay.
took 2. Yeah.
No, that is different. So this is a different thing than before. So we know that FE star R red is
Yeah.
a finite over R reduced. FE star R red is finite, or F star R red, there is no E required here.
Yeah.
So F star R red is finite over R reduced. Yes, because of the assumption on finiteness of R. And then there was, sorry. E is required because E is the number that we had before, right? The map factors through
R.
R. Yes. So we need E for that. Yeah. So that is one thing. And we need to show that the map from R reduced to FE star R is finite.
Yes, that is what we want to show.
That is what we want to show. Now, if we can show that Fe star J is finite over R reduced, then
Yeah,
we are
then
done.
yeah.
Okay.
So,
So because yeah, enough to show that Fe star J is finitely generated over R reduced. So we want to do this. Now let's go back. Go to the top.
yeah, this J mod J square thing.
Yes. Here, applying Fe star.
Yeah,
mm,
so this is finitely generated.
I think
This we can write as R head.
okay, now I'm taking K to be K equal to first. What if we put K equal to N?
Yeah.
That is going to be Jn minus 1 n minus 1 to R modulo R to R mod J power n minus 1.
Oh yeah, sorry, yeah.
Jn minus 1, right?
Yeah.
Oh, but this is also not right.
No, but proving that Fe star R is finitely generated over R red, it's
Yeah.
helpful to prove these two things are if you apply Fe star. But I think if you apply Fe star here, it is 0, no?
Fe star of Jn minus 1. No, Fe star is an exact functor. It does not
Yeah,
it does not
okay, yeah. The
take it to
action is
non-zero
0
elements.
maybe.
The action is 0, yes, but we won't show that this is finally generated over R reduced. Okay.
The
So
action is also
once
not 0. Okay, sorry.
yeah, that is not usually the case. Let me see how I got it before.
But yeah, so this being finitely generated is equivalent to these two being.
Hmm.
And what is the next step? So I think we need to prove this is separately. And suppose that is done, then we have this.
At the end, you will have
That each successive quotient is. Yeah, if we prove each successive quotient is, then we will be done then. Because this thing in the end will be reduced to R red.
yes, but uh,
More R red we know. Because it is F finite. So I think yeah, maybe we can make this claim that enough to show that Fe star J to the K mod J to the K plus 1 is finitely integrated over R red.
Oh,
There is some doubt.
okay. Just 1 second. I think I may have the solution. Is that true? Is that true? Yes, it is true. Yeah. So this actually, this enough to show part is. Suppose this enough to show part can be shown. Okay.
Yeah,
Suppose Fe star of J power K mod J power K plus 1 is finitely generated over R reduced for all K. Then
yeah.
taking K equal to N, do we take K equal to N first?
N
Which one
minus
do we
1.
take?
Yeah.
N minus 1. Then this is just Fe star of some J power N minus 1. And to R modulo J power N minus 1. And what do we do now? We want to show that Fe star R is Fe star R is no. Oh, okay. So Fe star of J power K mod J power K plus 1.
Hmm.
Uh,
Yeah, I
yeah.
think if we prove this, then we are done. Suppose.
How?
Because I think Fe star R being finally generated is equivalent to Fe star J minus 1 and Fe star R mod N minus 1 being finally generated.
Sorry, Fe star. No, I don't understand. What is it that you said?
So if we apply the functor Fe star to this exact sequence,
This J power K minus K modulo J power K plus 1 to R mod J to that sequence?
no, suppose J to the N minus 1 R to the Jn minus 1.
Yeah, okay.
So in that, Fe star R is finitely generated if and only if the left and right modules are.
Yes.
But so this thing corresponds to taking the value k equal to n minus 1 here. Then we go to
Let
R mod
K.
j to the n minus 1. Yeah, so
Yeah.
but then suppose this we have.
Yes. So this is all contingent on the fact that so then we have to show that R mod J power n minus 2 is finitely Fe star of that is finitely generated over R. At the end of the sequence, we will have something like okay.
Yeah, R mod j. Yeah.
Okay. Yeah, I got the proof. Yeah, okay, sorry. Let's see. So J power K mod J power K plus 1, right?
Yeah.
Is R mod J module.
Yeah.
It's a finitely generated R mod J module.
Yeah.
Module. And therefore, Fe star of J, this whole thing is finitely generated.
Fe star R.
Is finitely generated Fe star R module. Fe star of R red module.
Yeah.
But Fe star R red is a finitely generated R red module.
Yes.
That is yeah. Therefore, it is a
Yeah.
finitely generated R reduced module.
Yeah.
Finitely generated over R reduced. Since R reduced is finite.
Yeah.
So yeah, once we have this, since R reduced is finite. So once we have this, then using the short exact sequence, starting with k equal to 1, because you want the left modulus J mod J square and the right modulus R mod J, which is R reduced, both of which are Fe star of these left and right are both finitely generated over R reduced. Therefore, the middle is finitely generated over R reduced. Keep on repeating that. At the end, you are going to get Fe star of J power n minus 1 mod Jn, which is J power n is being 0. On the right, you have Fe star of R mod J power n minus 1. And by induction, both left and right are finitely generated over R reduced. Therefore, in the middle, which is just Fe star of R, therefore it is finitely generated over R reduced. And so we chose E such that the map R to Fe star R factors through R reduced, and we showed that now that this map is finitely generated, therefore the composite is also finitely generated.
Yeah. That I think gives the complete
Yes.
picture. Yeah.
Yes.
Okay,
Right, I
it's a
can.
nice exercise, I believe, and maybe useful
Uh,
also.
I forgot about that. This logic, like j power I mod j power I plus one. So this, why do we care about the quotient, these quotient pieces rather than say j power I? Because we can't see the j is an ideal in R. So powers of j are also ideals in R. There is no map from R reduced to this. There is no action of R reduced on these powers of ideals of R, So that is why we consider j power I mod j power I plus one, because that has a natural R mod j structure. So that is why we can say that, okay, this is an R reduced module. Let us see if this is finally generated over R reduced. We can't do this for some, we can't apply a phi star to J to R mod J.
Yeah.
You because that is also a short exec sequence. J to R mod J. R mod J is R reduced. You can then say phi star R. We want to check whether it's finally generated. Let's see if phi star J is finally generated over R reduced. But that is not that is not the way to go, because J is not even an R reduced module. Phi star J need not be an R reduced module. So yeah.
Yeah. Okay. Yeah, this was, I think, something nice.
Yeah.
Okay, I think, yeah, maybe we can stop.
We'll stop now. Yeah.
Yeah, maybe how to stop recording, do you know? I don't see, I think.
There should be an option called record. Yeah. You can click that and
Like, stop sharing first of all, and yeah, it's not showing up, but I believe, oh yeah, there it is. Stop recording.